The hallmarks of aging could be understood more as a network. It's a systems biology network. Typically, if you alter one hallmark of aging, it ripples through the other hallmarks, or multiple other hallmarks of aging, more or less. So it's difficult because if it's this interconnectedness where influencing one influences others makes it difficult to pinpoint ones. However, I do believe that there are some that are more prominent overall and certainly in context-specific ways.
Welcome to Longevity by Design, a podcast designed to give individuals access to the leading scientific information in the field of longevity. The ability to add years to your life and life to your years needs no opinion. Join us as we ask science to take the wheel. In each episode, Dr. Gil Blander joins a co-host and an industry expert in the field of longevity, shining a light and getting the answers to the key question: how can we live a longer, healthier life?
Hello, I'm Dr. Gil Blander. Welcome to Longevity by Design, how to live longer, healthier life. We are produced by Inside Tracker, your science-based guide to optimize your body from the inside out. Our guest today is Dr. David Barzilai. Dr. Barzilai is a physician and the founder and CEO of Barzilai Longevity Consulting, an healthspan coaching company widely regarded as the authority in longevity medicine. Dr. Barzilai integrates evidence-based practices and advanced knowledge in aging science to drive innovation in healthspan optimization. Dr. Barzilai is an inaugural faculty member and trustee at the Geneva College of Longevity Science. He holds an MD PhD from Case Western Reserve University, a PhD in health services research, and a rigorous training in evidence-based medicine. He also earned an MBA from the Eisenberg School of Management and is a diplomat of the American Board of Lifestyle Medicine, bringing cross-functional approaches to advancing longevity science and healthspan strategy. Dr. Barzilai, known as Aging Doc on X, formerly Twitter, has a following of over 35,000 individuals, including many researchers and clinicians in geroscience, aging biotechnology, longevity science, and lifestyle medicine. Through this platform, he brings together clinicians, researchers, and industry leaders to drive cutting-edge advances in aging science and healthspan strategy. Dr. Barzilai works in advancing personalized health strategies and shaping longevity best practices has established him as a transformative leader in the science of living longer, healthier lives. Welcome, David.
Hi, Gil. Great to be here. Thanks for inviting me.
No, that's a pleasure, and I know that was a long pregnancy. I was trying to recruit you for a few months, and I'm very excited that it's finally happened, and looking forward to hear your wisdom. So before we start to dive into the science, I would like to learn more about yourself and know what led you to become a scientist.
First, a compliment to Gil. I've been approached by various individuals, and I've consistently said no, except for my original introduction to the community. But with the quality of the platform you have here, bringing aging scientists around the world, I was honored to be here. So, what led me to become a scientist? I mean, it's like a twinkle in our eye when we're toddlers, right? We tend to be curious and wonder how the world works. And I was fascinated since I was a young kid about astronomy. I would devour books by Carl Sagan and the science fact books by Isaac Asimov and others, and be curious, what is it, these little ants, what makes them go, and biology. So my other passion, besides just being a voracious reader and being an aficionado of the old stacks back when people visited libraries, it's basically my other major passion is people. I love to help people. I love to work with people. I was one of those kind of goody two-shoe kids that really loved to learn, but also enjoyed helping people and holding the door for people and things like that. So it seemed to me natural to combine the two as a physician, where I could apply the science, which was like a life where you're constantly learning and innovating, and do that directly to help people. So from an early age, I thought, well, an MD, PhD is a pathway that made sense to me. So I went to the University of Rochester, where one of my 2 degrees was a BS in cell developmental biology. And that was everything else in life was like, it came easy because I worked so hard at the University of Rochester. I was doing 2 degrees in, molecular biology, biochemistry, cell biology, developmental biology. I took a graduate course in immunology and was very proud not just to be the only undergrad taking it, but to have gotten an A and one of the highest scores in the class. They gave me permission to do that because I liked, rather than being a broad BA, for it to be a BS and with more rigor. So I had a real formidable experience. Like, you're asking about the story about the science. I still, like, if you're out there is a professor, David Goldfarb. He was incredibly inspiring, utterly brilliant, and brought the best out of everyone. And one day, outside of his office, I just saw him sort of swoon backwards with an envelope, back when people got mail, and fall backwards with an astonished look in his face, and like, So I literally ran across the hall. Are you okay? What's going on? And what he told me was, I got my grant. He literally held the envelope up. And that was really the first real eye-opening experience for me as an undergrad. The immense pressure, even for people as brilliant and prolific and industrious as David Goldfarb. So ironically, that's sort of consolidated my commitment to practice medicine, applying the science, because I love the science and learning the science, but not necessarily applying for grants. And I love teaching, but not necessarily all the responsibilities of running a lab. So ultimately, I did pursue an MD PhD, but what I was very interested in making the aging biology and biology relevant to patients. So it just so happens, for one of the programs that I applied for was Case Western Reserve University, that's down by the Cleveland Clinic. We all know them, and university hospitals. They gave a letter to everybody who was already accepted, and they said, we're creating a new program. It's just like MSTP, so it's an MD PhD program, except you're going to be funded by a T32 grant in health services research, the first of its kind, housed within a department of epidemiology and biostatistics. So what made this unique, it's the first program of its kind in the country where it's, for those who don't know, health services research, it's like outcomes research. So it's everything: cost, quality, outcomes, randomized control trial, clinical research. So I'm like, perfect. Science applied to patients. And at the same time, because we'll get to that later, but I've been very passionate about longevity science since before being an undergrad. So I kept reading my basic science long after my BS for multi-decade, which is how I have such a breadth and depth in aging biology while doing health services research. So long story short, in my department, I had multiple chairs in my committee: chair of the Department of Epidemiology and Biostatistics, chair of the Department of Dermatology, program director in gastroenterology, to use SEER Medicare linked data for essentially to look at variation, which ultimately couldn't be adjusted for, in surveillance practices. And this started my interest in sort of what is evidence-based medicine and what is precision medicine, because it didn't make sense, the variation that was being done, because there wasn't much evidence. So while I was a graduate student, I was prolific. I would say about a dozen peer-reviewed publications came out of, only 3 of them related to my PhD, but mostly, a mix of first authorship, second authorship, and top peer-reviewed journals, all with the effort for me to have a diverse set of experiences. And so I learned conceptual models as well as biostatistics and application. And ultimately that culminated in how I use this sort of thinking, breaking down a hard problem into pieces so I can apply it towards evidence-based best practices around longevity medicine. So that's kind of my story in science. And of course, if you're true science, it never ends, right?
Yeah. No, I agree. And I think that it's very important to have the translation, to have someone or to for clinician like you to translate the science into practice, because a lot of clinicians basically, they know what they learned 10, 20, 30, 40 years ago, and they are not applying a new science. And what you are doing on X, we'll discuss it later, and your approach is very important because I went to my clinician and told him that I want to test for ApoB, or I tested for ApoB, and they asked me, what is ApoB? So it's get to that situation, and I think that it's very important to have people like you doing that. And let's now get into the meat and potatoes. So what sparked you to your interest in longevity science and health span?
That's a very personal experience. And it's interesting, we're talking about doctor stories like, they don't know ApoB or they're not familiar with Lp(a). It's really sad. But my own personal experience in terms of interest in longevity and aging, besides always, it sort of came out of early experiences, very early experiences, out of existential dread and life being finite, and also personal experiences. So basically, I remember when I was very young, this was like early elementary school, a teacher making a kind of casual mark like about people can die from loneliness. And somehow that thought stayed in my head. Part of the thought was like, what's the mechanism for that? I was always like, that can't be true. But also as my teacher was like, I hope it's, it's like, how can it be? And that stuck with me, and that became even more powerful. It was one day when my father is an interesting guy. He's like a brilliant engineer, sort of taught me engineering principles, think like an engineer, schooled at the Technion. But he came home like out of breath and said, terrible news. And it's just to be the shock of someone like your father rushing to their terrible news. And your grandmother died. And of course, my first thought was, my grandmother, she lived in another country. I was born in the US. I lived here my whole life. That's the only country I ever knew. So I never really knew her well. So I just felt really sorry for him. But the other thing that was shocking to me was just like, I knew about life being mortal and already was like kind of in my head, but how sudden it was, just how unpredictable life is. I do actually have like something that really was profoundly impactful, like genuinely. So I had severe asthma as a kid. By severe, I mean, they had to put me on long-term steroids, which not a lot of kids don't have to be. Most are just like albuterol. I had a series of, I was constantly going in and out of the hospital, sometimes an overnight admission, giving epinephrine shot. And that was a really shocking, traumatic experience. The doctor report wasn't always the best, so it made me all the more wanting to be, hey, maybe I could be one of the good guys who actually talks to people, explains what happens, treats them like they're intelligent, like, involve them in the decision-making process. But I was also phenomenally grateful that the doctors saved my life. You know what I mean? They saved my life, not once, but a bunch of times. But that experience of, for anybody who's really been hypoxic, out of breath, where you have your risk for respiratory failure, where you just don't have enough strength left to continue those deep inspiration, you really feel like, and you are gasping for your life. So that would just underscore just how pivotal health is, both for the quality of life, which stunk, and also just to survive. Plus, it was extremely limiting too. I couldn't play any sports for fear of getting asthma attack. Made me feel vulnerable. But ultimately, all these things just made me aspire and not just have a obsession, if you will, for health and longevity, optimizing that and really using science for best practices. But ultimately, it became my inspiration to help others through my current longevity practice.
Yeah, no, it's a good story, and actually my story is similar. I had a death in the family, and actually my son also has asthma. So I see and hear you again, not from a first degree, but I see it with my son, and it's really worrisome to have something like that, and to basically worry on something that for everyone else is a given. It's easy to breathe. Why should I think about it? So it's a very good story, and I assume that everyone in the world have something like that made him aware that we are not immortal. And some of us, like you and me, took it to the extreme and working on that. Some others saying, "Oh, it's in 50 years. Why should I worry about that?" But yeah, so
very, very personally, before your next story. So I would say the great, I see myself as essentially practice as a geroscientist without a lab. the monitoring. So I apply geroscience, but most, even in the field, I don't think necessarily have so profound an experience. I remember every night going to bed and seeing the little crack of light under the door and thinking like, another day is going by. You know what I mean? Yeah. But I try to ground everything I do based on sort of real science rather than wishful thinking. So, but to a very aspirational kind. So, yeah, it is very personal.
Yeah. Yeah, and I have to say that you are taking the time very seriously. We are meeting today early morning. You can see the sunrise in the back of my...
It's beautiful.
Yeah. It's not yet there yet, but I'm saying you are a very serious person, taking time very seriously and trying very hard to help people live better, longer. So I really appreciate it. And that's taking me actually to the next question about one of... the most impactful, I think, activity that you are doing is the Aging Doc on X or Twitter. And basically, for me, if I want to get an update of what's happening in the world of longevity, I'm looking at your feed on Twitter, and I know exactly what happened, what was published. I assume that it's a lot of work. You're spending a lot of time. And by the way, I recommend everyone from our listeners, if you are interested in longevity, follow David on X or Twitter, and you will know everything that's happening in the longevity field and every paper that was published. Both
good and bad. And bad. I'll get to that, but the purpose isn't for me to vet it, but to foster a community thing. But I appreciate seeing your background. People who are watching don't know that we're almost literally neighbors. I grew up in Lexington, and I went to Lexington High School, a fantastic school, and right next to you, Gil, in Lexington. But I never sought out to be the legendary aging doc or to be a social influencer. I don't see myself as a social influencer at all, but a scientist and a clinician. But basically, it started from something pretty fundamental. I had this passion for health and longevity my entire life. That led me to become a doctor and many other things. So what I started to do, or I have done all along, is I read deeply in the aging biology literature. It wasn't even called geroscience then. It was called biogerontology or biomedical gerontology or by other different names, and also lifestyle medicine. And I looked to apply evidence to decide for myself, because through my PhD studies and evidence-based medicine and biostatistics and reading the literature, I read the primary literature on my own, because reviews are often very wrong or misguided or incomplete or have an agenda. And I was going through a phenomenal amount of time. Like I was in a specialty where I had banker's hours, which left me hours every day to pore over the literature. And what I started to do was I saw, hey, why not just simply post things that are encountered that are crossing my desk, not to whether it's a good study or it's fatally flawed, just to put it out there so that there's a central repository, so that individuals interested or in this space, such as aging biologists, for example, are aware of what's circulating. And if it's a bad study that's circulating, they can communicate with the media or others in their circle of influence to say, hey, this is a bad study, and here's why, and here's what you should know. That was economical. It's time efficient for me just to post, rather than share how I really feel. So the objective was more not to dictate what to praise it and spoon feed, but rather to create a community with a ethos of community, examining data, if there's hype in an article, discussing that hype and not generating your own hype or personality politics, one free from agenda. Some people have products and services specifically around what it is that they're posting. And I thought, hey, it seems to have resonated with people, as I have a lot of my core followers have been aging biologists, geroscientists, and clinicians, and other members of longevity science community. But it's Aging Doc 1. And just remember, read the study for yourself. People are asking for summaries and AI generate. No, the point is for you to read the study, understand it, and make up your own minds. to do so based on data, not to try to defend your a priori belief on what the best diet is or something.
And don't be lazy. Read this, the paper, and AI make a lot of mistakes, and there are a lot of gurus outside that taking one paper and making from him, this food is very bad, and that's it. No, it's not like that. It's more complex. There is a good and bad in everything.
Or at the very least, because I don't expect everybody to have spent as many years with these skills vetting the literature, which is a different level of advance than even your typical internal medicine or other grounded physician. It's at the very least, don't believe it by default, and inquire with knowledgeable authorities and do your own diligence and make up your own mind. But I think that's what it's about. And I'm very proud that when I went onto X, I had 0 followers, and nobody knew who I was. So some people get big followings because people know them for real life, but I grew to tens of thousands of followers. Nobody knew who I was. And I think that wasn't just because it was a useful service, but also one where every so often, when I thought that the benefits exceeded the badness for the community and did not good, I'd hint that I would give some information about my own assessment of something every once in a while, but it was sufficiently in-depth, like, wow, this person really knows what they're talking about. They're not just posting things. I think that's been the secret pudding, that there was that, and keeping things objective and transparent.
Great. Thank you so much for the great introduction. And you mentioned before the term biogerontology. So can you define it? What is that?
So biogerontology is a scientific study of the biologic aging process and how it influences longevity. So it integrates a wide variety of disciplines. There's genetics, there's molecular biology, there's human physiology, even evolutionary biology, all these different fields. And they all come together to look at what are the fundamental mechanisms of aging biology that drive the system's decline, loss of functional health, age-associated morbidity, mortality over time. So to do so, they look at mechanisms such as cellular senescence, epigenetic alterations, and so forth. And by doing so, they're hoping not only do they understand the mechanisms, but potentially actually apply these things towards potential therapeutics that can extend healthy longevity. So ultimately, biomedical gerontology, biogerontology, some people might say there's a little bit of a nuance, but it's often used interchangeably with geroscience. And that's as opposed to gerontology, which is just a study of older adults. Biogerontology studies the biology, and moreover, it's a process that starts at birth, or starts with our parents, with the genes there, or starts with our grandparents, because there can even be some epigenetic things from our grandparents. So it's looking at all of these mechanisms to look at how to promote longevity and reduce age-related decline, dysfunction, morbidity, and mortality.
Yeah, so that's great. Very good definition. I haven't heard a better definition before about that, so thank you so much for that. And you started to mention epigenetics and maybe senescence, and all of that is part for the hallmarks of aging. So can you define what is that? And is there one that is more important in your opinion?
Okay, great questions. So in aging, we have a progressive decline in our physiologic function, and with it, their counterparts at the molecular, cellular, or tissue, organ, and systems level. So essentially, we end up, as a byproduct of this, having increased vulnerability to disease and death. So what the hallmarks of aging are is they're essentially explanatory models or mechanisms that can explain this aging process and hopefully potentially ameliorate it, as I alluded to with your last question. So it's an evolving framework. It was originally in 2013 when Lopez Oten and colleagues, they had a Sentinel citation classic. The most famous in our field as geroscientists, called Hallmarks of Aging. There were 9 then. It's been updated to 12. They created 3 more which was related to the microbiome and inflammation. And they made autophagy an additional one before that was lumped into with altered proteostasis. But they're like, altered proteostasis, that's protein, but autophagy also acts on organelles and recycling of nutrients. So all of this suggests that this is really a work in progress. The hallmarks of aging are very incompletely understood. And there are many more out there. So something that thought leaders such as, for example, Matt Kaberlein, Vadim Gladyshev, and others, and Pedro, they point out, well, the hallmarks, they're not as concise and unified as the hallmarks of cancer. They're a little bit more arbitrary, and we don't want to be spending all of our time looking under the lampposts. At the same time, so we should be looking for other discoveries. But at the same time, how are they useful? How are these hallmarks of aging useful? Well, what makes something a hallmark of aging is basically 3 criteria, albeit some arbitrary natures of it. One, that it correlates or goes up with aging. Makes sense, intuitive, right? The other is that if you exacerbate this hallmark of aging, you accelerate phenotypic markers of biologic aging. And the third, which is the hardest to prove, but all of the hallmarks have at least some evidence in this regard, is if you can improve that hallmark of aging, make it less deleterious, make it less present. So this could be, altered proteostasis. This could be epigenetic alteration. This can be mitochondrial dysfunction. It can be cellular senescence. It can be genomic instability. It could be mitochondrial discomposition. The 3 others I mentioned, even telomere attrition, altered intercellular communication, et cetera, et cetera. What are they? If you can do something about these things to make them actually better, will that model organism, by some phenotype, seem to be biologically aging more slowly, or even potentially not just slowing it down, halting, or some phenotypic measures of reversion? Nothing's led to complete reversion at an organismal level, maybe at a cellular level, more or less. But that's the power here. So number one, it gives us an explanatory model. And when I was getting my PhD, these conceptual models are really fundamental to asking the right questions, because if we don't ask the right questions, then we're going to get garbage it. We're going to get garbage in, garbage out. Secondly, it helps cynically. It's a way to both explain the fields to other people. And it's a way to get grants, to say, I'm going to target this hallmark, I'm going to target that hallmark. But in a relevant sense, it gives us potential targets to aim for. Yeah, but just we need to remember that they're very incomplete. So we shouldn't be blindsided, look under the lamppost like the blind person looking for their keys under the light. And why are you looking there? Because that's where I can see things. They're not looking in the dark areas where their keys might have fallen. Yeah. So regarding your other question, it's important to understand that the hallmarks of aging could be understood more as a network. It's a systems biology network. Typically, if you alter one hallmark of aging, it ripples through the other hallmarks, or multiple other hallmarks of aging, more or less. So it's difficult because if it's this interconnectedness where influencing one influences others, makes it difficult to pinpoint ones. However, I do believe that there are some that are more prominent overall, and certainly in context-specific ways. So an example of the interrelation I'll just give. So let's say you have genomic instability. That's like DNA damage and things like that. And that in turn, let's say some transcription factors for mitochondrial biogenesis and mitophagy are disrupted. That's formation of new mitochondria from fission, or mitophagy, the autophagy of gobbling them up. That in turn can lead to a senescence phenotype in that cell. So that cell in turn will produce SASP, senescence-associated secretory phenotype, which in turn produces inflammation, reactive oxygen species, etc. But in answer to your question about a couple that I think are more, that are, if you can have some relationship or some, one of them to me is the mitochondrial dysfunction. I mean, the mitochondria are really key it's not just for energetics, where we need adequate energy availability, but they are active in reactive oxygen species dynamics. And I say reactive oxygen species dynamics because excess reactive oxygen species, we've heard, public knows about free radicals and things like that, can be very damaging to multiple hallmarks of aging. At the same time, they're also important signaling molecules too. So it needs to be honed in just right. And another major hallmark is one that's one of the three new ones in the revised classification system. And that's inflammation. In fact, in functional medicine, for all the inflammation is the root cause of aging. I'm like, mostly, well, it's very important, but there's a broader hallmarks of aging. And the reason that inflammation is so important, there's a classic publication where the term inflammaging was coined, where acute inflammation is relevant and healthy, like a boost in IL-6 right after exercise is adaptive. You need it for tissue repair. You need it to properly mount an immune response, and then clear cells, etc. But pathological low-level chronic inflammation is associated with the supermajority of chronic diseases. So it is both produced by the other hallmarks and also greatly catalyzes the damage of the other hallmarks. So in a nutshell, the hallmarks of aging are explanatory mechanisms that are incomplete, and those are a couple of the more important ones in this integrated systems biology between the network of hallmarks.
Yeah, a very good explanation. And just to double click on the inflammation, at InstaTracker, we have a database now of hundreds of thousands of people, and we basically looked at them at PCA analysis, and basically found two different locations of high inflammation, looking at the hsCRP, which is a well-known marker of inflammation. And when we try to understand why do we have two different locations, we realize that in one of them you have more people that are exercising and active, and the other one is more like a population that are more sedentary and look like they are more sick. They have a higher cholesterol and a higher A1C and so on. It's fit very well to what you said. Yeah, IL-6 is going up when you exercise. That's actually good, but there is also the bad inflammation, and we're starting to understand that inflammation is like what we said before. Nothing is good or bad. It's like depending on the context, and that's why system biology is so important.
The right dose, the right amount, etc. Because chronic IL-6 is bad, so is TNF alpha, IL interleukin 1 beta, and all these others. But it's like what the right dose, and then you can have these hormesis, which some people don't love that term, but it is a real biological phenomenon that the Dose Response Society has a lot of research that they focus on. But it affects all of systems biology. It all comes down to signaling and information. So we want to preserve an adaptive homeodynamic network rather than homeostasis where everything is fixed.
Yeah, exactly. And if we are still staying on exercise, so exercise is great, but it can be bad. If you are exercise too much and you become injured, that's not good. So everything should be in balance, and nothing is very good or very bad. It's all in the context of what's happening around.
Everything is like J curves and trade-offs, like antagonistic pleiotropy. What might help you when you're young might hurt you when you're older. And that's part of the art, actually, of this field and the precision medicine.
Yeah, and another quick point, the other Barzilai, Nir Barzilai, is always
no relation. Yeah, by the way, I consider him a brother spiritually. Like we're on the right battle for the geroscience hypothesis, rather than playing whack-a-mole with all these diseases so late in the game where we can hardly do anything. Let's affect the fundamental biology of aging. Yes, about Nir.
So what Nir is saying, which is very interesting, you said metformin is good, but it's good for people above 65 or something like that. Don't take it when you are 20. So it's the same. It's like the context is the age, is the activity, and everyone need to understand that biology is so complex, and we need to understand what's happening below, and you cannot say that metformin is always good or anything else. I assume that we'll discuss it later, but I think that it's a good anecdote to know. And if we are discussing on the hallmarks of aging, There is a lot of data that coming from a model organism, specifically for mice, and there is the ITP study of the NIH and other. So what is your opinion about the translation value of those data to humans?
And that's a great question. Of course, I think we should remind ourselves first that there's no maximum life extending validated therapy in humans currently that's at least been validated. There might be there, just not necessarily valid. The closest thing we have to that is lifestyle medicine, which may extend maximum by a little bit if it does, but mostly prevents premature mortality, which is phenomenally important. We don't want to die early from heart disease, dementia, cancer, and so forth, some of our top killers. So it's not surprising that the first application, when we start with the most evidence based on the most kind of scientifically cutting edge, more recent areas where we're moving towards, is that if you have mice that, like humans, are obese and sedentary, guess what? They die early. That's highly conserved. So what is it that makes mice a useful organism? Well, first of all, I mean, there's phenomenal conservation from our simplest animal, our model organisms like worms to human beings, where a phenomenal number of genes and mechanisms are in common. But mice, they're vertebrates, they're mammals, so they're genetically similar. They're short-lived and they're small, making it possible to do experiments efficiently and cost effectively. And they're also tractable for genetic interventions and other interventions that would be hard to test in humans, at least at that stage. So they're phenomenally useful. Now, some major applications or similarities between mice and humans on the application side. First is caloric restriction. In the 1930s, Clyde McKay basically uncovered that if you caloric restrict mice, you can get up to 50-60% median lifespan extension at really extreme levels of caloric restriction, levels that wouldn't be achievable in humans or good for us at the brink of starvation. Now, they had a much more modest intervention in humans. It's a series of trials people refer to the Calorie trial. There are actually a bunch, and it's across different institutions, across different years. But among the Calorie trials in humans, they wanted humans to reduce calorie intake by 25%. They were only able to achieve about 12%. And they found not just weight loss, but similar metabolic adaptation. Some of the hormonal milieu, including along the insulin IGF-1 pathway, was similar. And they also found not just this, but that markers of inflammation, lipids, and even markers of oxidative damage. For example, you can measure in the urine F2-isoprostane, which is a measure of peroxidation of lipids, which is reflective on oxidative damage. And there are other markers they measure in the urine in terms of DNA and ribonucleotide damage. So all of this paralleled mice nicely. Now, should we be doing this in humans? Even if we could, because compliance would be a huge issue. There are issues there, right? And everywhere from sarcopenia to vulnerability to infection, wound repair, even in predisposed populations psychologically. But the point is, it's inspired this idea of caloric restriction mimetics that could ideally recapitulate some of the phenotypic benefits of caloric restriction without some of the downsides as a pharmacologic target. So that's one example. Another example is along the mTOR pathway, the 2009 interventions testing program establishing a 14 and 9% a median average lifespan extension for 14 for the female, 9 for the males, was really phenomenal, not just because it showed an increased lifespan for the first time in a pharmacologic intervention highly well validated through NIA's gold standard study, where you have 3 institutions. They were heterogeneous mouse breed and Het3s instead of black 6, which are clones, and worse than being clones, there were clones. There were homozygotes at all alleles. Biologists will know what I mean there. It's the kind of thing we try to avoid in humans, where we have a founder's effect and people inbreed. And sure enough, these black 6 are highly vulnerable to all sorts of genetic defects. Anyway, it's a huge study, 3 institutions, robust results, and it's genetically diverse. And through a matter of just luck, that in that intervention, they couldn't get the formulation to work. They had to enterically coat it so it wasn't dissolved to reach the endpoint. And as a result, rather than introducing that molecule early in life when they attended, because nobody at the time thought it's already a stretch to have something like a pharmacologic intervention that extends the lifespan in mice. But to have one in old mice, I mean, the damage is already done. You got to start early. Like caloric restriction only works well in young mice, so a lot less in middle age and not at all in older mice through work by Rick Weindruck. But anyway, getting back to the model, it showed that late life, because of that they couldn't get the formulation to work, they had to give it to mice that were older. Like, well, I guess we'll give it to them anyway. It won't work, and it worked. So that application for late life extension, we don't want an intervention that we can get as kids, right? We're not kids anymore. We want something we can give to adults. So that's an application that's showed promise in humans. And as a result of this, and we can go in later, all these different things that have been studied, heart function, some cognitive dysfunction models that are genetic models, oral cavity, cancer risk, etc. Was a classic study by Joan Manick and Lloyd Klickenstein in 2014. This is back in the Restore Bio days. A lot's changed then for Joan Manick, and now she's head up Tornado. But what they found in this preliminary result was that if you give rapamycin for 6 weeks, it actually wasn't rapamycin. More precisely, it's a rapalog, everolimus, another mTOR inhibitor, extremely closely related, another mTOR inhibitor. Give that either daily 0.5 milligrams or 5 milligrams once a week or 20 milligrams once a week for 2 out of the 3. The first 2 ways they were able to show increased titers for their endpoint, 2 out of 3 titers for increased immunity. So long story short, a measure of immunity in this older adult selected population in this randomized control trial, they had a boost in immunity. They also self-reported fewer infections after that study too. But that objective titer, their primary endpoint, was met. So that's exciting. That to me is indicative of a potential translation in humans. Now the evidence since then has been mixed, and that's a whole long, complicated story that would take us probably more time than we have. The FDA moved the goalposts from objective markers to symptoms, which are very non-specific. They chose another population that was less which had less power because of less prevalence, and they used a little bit of a different formulation, so it didn't test the same thing. But those are a couple of exciting examples, and I think for the sake of time, I can talk about canagliflozin and metformin later, which and other things. I'll just do a couple of other exciting applications. I'll just name one more quick translation because I think your audience will find it very interesting. So you know how we were saying that the insulin IGF-1 pathway is highly conserved, like from Tom Johnson and Cynthia Kenyon, who's now with Calco. They're finding a doubling of lifespan through just a DAF2 mutation, age 1. Well, if in mice, which you can genetically modify, there are these dwarf mice, Snell dwarf mice, Ames dwarf mice. They have a defect where the anterior pituitary, it doesn't form properly. So as a result, this signaling pathway isn't working well in them. It's interesting that these mice, they're very small, but they live very long, and they're protected from multiple age-related diseases, including cancer, for example, and just general multiple different hallmarks of aging, and they live substantially longer. So in humans, there's a population that has Laron syndrome. There are a couple places in the world where they're in greater concentration. One of them is in Ecuador. And the individuals with Laron syndrome were found naturally. And what they had in this syndrome was they were lacking growth hormone receptor. And as a consequence, that receptor is mostly in the liver. It's in some other places in the body too. But as a consequence, their IGF-1 level is low. And these individuals with this genetic issue, they have virtually no cancer. Even though they're obese, there's a lot of obesity. A lot of them are smokers, have very unhealthy lifestyles. They have almost no diabetes. And there's actually some preliminary research suggesting that they may also have less neurodegenerative disease also. That's not as well validated, but there's a suggestion of that. Now, they don't necessarily live longer. It's, I mentioned that they're very short in stature. They're very petite because of this. And they actually have a very high prevalence of accidents and injury. So we don't have great long-term mortality data, but at least some of the common causes of death, and they have a lot less morbidity. So this suggests to us genetic things that can be modified. And later, at another question, I can go all into metformin and your point, like if you're an athlete, you don't necessarily, if you want to look big, you don't necessarily want to go on metformin, because in people who are exercising on metformin, you have less gains in VO2 max, a marker of aerobic capacity, and also you have less muscle hypertrophy. But it's interesting, on metformin, they weren't any less strong though. They just you don't have less muscle hypertrophy. And when Barzilai did some research into this, he found that basically you have all these omics. You can look at the translation, transcription, etc., and that their overall pathways resemble much more that of younger individuals than older individuals. So there might be a trade-off between performance and sort of long-term resilience. An example of antagonistic pleiotropy. And even just only a couple months ago, there was an important study on primates where these primates were they were approximately the age of 40 or 50 years old in human years. And these primates were given metformin for what would be the human equivalent of being it for about 10 years. And you were able to see radiologically less aging over that equivalent of 10 years. It was really 3.3 years for them. And these deep omic clocks, they reverted several years younger in biological age. And importantly, even functionally, they even did the equivalent of neurocognitive testing for them, and they performed neurocognitively better. Now, it's a very complex issue because the ITP by itself did not reproduce metformin, and effect size is modest in mammals, very large in small animals, and the therapeutic index is more narrow there. But on the other hand, we have a lot of great human epidemiology, and there's all this controversy. The UK Biobank showed that the diabetics on metformin did better than the non-diabetics, but then another study failed to reproduce that and found kind of the opposite. Bottom line is where we stand for metformin. I wasn't going to bring it up, but just because you brought it up, is I feel that metformin is very important for us to study, because we need to remember it's not just that only 10% of mouse studies translates to humans. It's also some things work for humans and not for mice. And we have a sufficient number of, albeit prone to confounding data in humans. It's very broad across different areas, coupled with intriguing phenomenon. Like, for example, if one of the sites had changed for metformin, then that ITP study would have actually been positive. And when you give metformin plus rapamycin in another ITP study, you had a greater lifespan extension than giving rapamycin alone at the same doses using historical controls. So this is an argument that goes forever and ever and ever, because you're like, those were historical controls. They didn't use real controls. How do we know if the mice were the same? Maybe it's not adding the metformin. And they're all legitimate points, but to me, that just means we need to fund TAME. Full stop. Fund your Barzilai's TAME, study metformin humans, and if we had time later, I can go into methodology and great depth, but it's basically they're using time to event to age-related diseases, which I think is brilliant on your part in the absence of an aging indicator.
Yes, so thank you so much for going deeply into this question, because I think that's a very important question, and I'll provide my perspective about it, that sometimes it is translatable, sometimes it's not. And I think that your point about the metformin, that showing that there are some not, but still we see it in human. And at the end of the day, what we care about is human. Nobody care if the scientists that do it, of course, care if metformin extend the lifespan of mice. But at the end of the day, all of us care about what metformin is doing to human, and we have a lot of data about it. So I think that we need to understand, in my opinion, the value of the model organism and use it, but take it with a grain of salt and understand that at the end of the day, what is important is what's happening in human. And the TAME study that near Barzilai one-to-one, and it's hard to find a fund for that, is so important because it's not only for metformin. That's will be the platform to perform a lot of other aging-related or longevity-related studies. So definitely, thank you so much for explaining it in so much detail. And going or following or follow-up of that is today we don't have yet drugs that treat aging. So the best tool that we have, in my opinion, is basically lifestyle medicine. And basically using your nutrition, exercise, sleep, stress management, and so on into our life. And I'm wondering, I would like to hear from you, what is your recommendation? How can a human apply it practically into their daily life?
Okay, so I'd like to dive into lifestyle medicine. I'm very passionate about that as a diplomat for the American Board of Lifestyle Medicine, which for people don't know, it's for people who are already physicians. They can take a deep dive into the curriculum. It's extra training with a formal examination, which actually is a lot more rigorous than I won't compare it with any other that I'll mention, but there are a lot of things that are kind of in the space of longevity and health, et cetera. And I've pursued a whole bunch of them, and this was the real science. With your permission, I just want to sort of illustrate, because I think I sort of was poo-pooing a little bit with the animal models. I think it'll be very interesting for listeners to see something very relevant on how the aging process is different in animals versus humans and how to capitalize on that. So the hallmarks of aging are largely conserved between different organisms, but how that they are conserved between organisms, those differences also can be harnessed towards increased and understanding mechanisms to improve and increase human longevity. For example, there was a study from Vera Gorbanova's lab on SIRT6, and SIRT6, it maintains genomic stability, DNA fidelity, and repair. And longer-lived rodents, such as beavers, have greater enzymatic activity for this than shorter-lived ones like laboratory mice. And what she did is she gave the gene to Drosophila flies of SIRT6, okay? And she gave one from beavers, one for mice. And mice live longer than flies, right? So guess what? Both variants lived long. The flies lived longer when they got the higher fidelity SIRT6 from the other organism. Isn't that incredible? So we literally can borrow from other species. Not only that, but the one that got the beaver, which is longer lived SIRT6, it lived the longest. And it does other things like repress transposons. TP53 is another example. We've all heard of P53 in breast cancer and other cancers, most common mutation for cancer in general. Elephants, they live a relatively very long time, and they have a ton of flesh, so they can't afford to get any cancer, right? We have one copy of TP53, and we have one copy. They have like about 20, depends on which. Like we were talking about one of two different African or the Asian elephant, the three major species. And as a consequence, they have low cancer rates. And an additional, like naked mole rats, they live much longer than other rodents their size. They live like 30 years. And naked mole rats are high in hyaluronan, and which also helps with wound repair and has a variety of other benefits for a burrowing animal. Like it's flexible, but they also have very good protein maintenance systems. And they also have very good DNA repair. And so hyaluronan, for example, is basically the combination of all those things make those organisms far, far less cancer prone. So I just want to explain to the listeners that it's not just, only 10% translates to humans. This lets us go through promising things much faster. But this field that I'm describing of comparative biogerontology can teach us so much more about these therapeutics for humans. Now, for lifestyle medicine, I'll keep it really simple. And then later, time allowing, I can give like all sorts of different statistics and specifics. lifestyle medicine is founded on the idea that you can have their evidence-based ways to extend your health span and your lifespan. And by lifespan, I mean mostly average lifespan to prevent premature death. So you can have a life closer to a species limit of a longer lifespan. It may affect aging biology modestly. That might be exactly how it works. A lot of us think that these things actually do work on aging biology, but modestly. But one example of the power of that is Life's Healthy 8. Life's Healthy 8 are a series of health habits, things like exercise, diet, stress, sleep. And for those who adopt all 8 out of 8 healthy habits, don't smoke, etc., if you compare those to the people who have none of the 8 habits, there was a recently published study that your average life expectancy for both men and women, do you want to guess how much longer?
I would say 10 to 12 years, but that's a guess.
I think 10 to 12 years is the correct answer. But what they found was over 20 years.
Wow.
Now, remember, this is an observational study, okay?
Yeah.
So, but I think even if some of this is confounding, right, that there's something about these people that they adopted these habits that made them healthier, besides those specific habits. Even factoring that in directionally, it's phenomenally powerful. And so they found 20 years extended lifespan, but the impact of health span, if it's maybe a 10%, let's say 10% expansion lifespan, the extension in health span, you can maybe have also a decade less with chronic disease and much greater health and robustness. So let's drill down a little bit. One recommendation that I see as a minimum ideal is 150 minutes of moderate or intense physical activity per week. That translates to 7.5 med hours per week. Those who do that tend to have better cardiovascular outcomes, including mortality. They have better metabolic health, lower rates of diabetes, and it goes with basically all of the major issues with disease. Those who have good sleep hygiene, who get typically 7 to 9 hours is ideal for most people. It varies by individual. They not only get those metabolic benefits we were discussing with exercise, but they also have better cognitive performance. They have better mood. And you have to think about things holistically, right? You also have better compliance with weight maintenance in that population. So you want to be thinking about simple steps like how to create a schedule that integrates these things. Now, for diet, for example, a diet, I think it should be precision, should be individualized, but there are certain common denominators. A diet that is based on whole foods, like minimally processed or refined, that also doesn't cause a large, what's called the postprandial glucose excursion, this blood glucose spike. Those diets tend to be better, and diets that have been relatively more validated for that are diets like the Mediterranean diet that in the PREDIMED study found a 30% lower risk of cardiovascular outcomes, including events and mortality. So that's another major thing. And I wouldn't underestimate stress. Stress elevates cortisol, and chronically elevated cortisol, paradoxically, even though cortisol is anti-inflammatory, ends up being pro-inflammatory, just like sleep deprivation is pro-inflammatory. And remember, we were talking about the inflammaging and all this problem, right? So I would not underestimate the importance of being surrounded by meaningful relationships with people who you love, who love you, who are supportive of your mental and emotional health, and also a sense of purpose. Because that sense of purpose often transforms distress to eustress. I'm always kind of intense. I have an intense, that was one of my secrets at college. I could study for 14, 15 hours just with bathroom breaks and snacks while I'm studying. And I'm glad that happened. I graduated summa cum laude, Phi Beta Kappa, and all these things top of my class. But the people who have a lot of a very high driven, like my clients in longevity medicine, longevity consulting, you got to remember this, that if you have a sense of purpose and meaning, that it can transform distress to eustress, and that alone can have a positive impact on health. So I'll just end the lifestyle medicine with a concrete example, and then later on we can go to more statistics and specifics. So my wife, she suffered for many years with both GERD, like reflux, and she also had irritable bowel syndrome, especially when she traveled, but on and off all the time. And I suggested a time-restricted eating window, restricting. She's Italian. She drinks 1 glass of wine a day. That's a whole other thing. But to not have that close to bed, not to have your meals too close to bed, not just, circadian alignment and all that. And it's interesting because Sachin Pand and others show that there's a lot of basic aging clocks. Aging and circadian rhythm are very, very linked. And if you actually improve the circadian clock, longevity increases in some model organisms. But at a real fundamental level, when your body tends to be warmer, when you're digesting overnight, and sleep hurts, and you're more likely to have GERD. So her symptoms improved, not just her GERD and her IBS, but also her sleep was better, and she subjectively reported to me that it helped with mood, and certainly she feels it and improved the quality of her life. So it's an anecdote, but it was she felt it impactful enough that she just stuck with it, like because she knows when she doesn't do that from experience, or so she tells me that she experiences those issues.
Yeah, and I think that what you mentioned, all those 8 kind of building block, I think that it's for me it's the 20-80 rule. Basically, that's the 80% of what we can do in order to optimize our life. But if you want to get to the top 20%, you need to do what we call precision medicine, basically to personalize it and provide to the user specific intervention that are specific for him and might not apply to other. And I would like first to hear if you agree with me, and second, I would love to hear your definition of precision medicine.
I would define precision medicine as tailoring to what makes someone unique. That is their genetics, their lifestyle, their environment. Tailoring and matching that to our interventions, which aren't just diagnosis and treatment, but are prevention. And I would say something else that makes us unique are our preferences too. Like we were just talking about my wife, right? So so one drink a day is fine. Like my philosophy in life is everything should be personalized and should be based on their own value system. So there's actually was a recent Surgeon General report about alcohol consumption, and the traditional guidelines are 1 alcohol drink a day or less for women and 2 for men, and some were saying it's heart healthy, and actually the data about it being heart healthy is very mixed. It's not clear. Some animal model organisms live longer with just the right dose of alcohol, but that might not translate to people, and it's debatable whether or not it does cause heart health based on the observational nature of those studies. And on the other hand, there's no lower limit for risk threshold that we've detected for alcohol as far as cancer. We found elevated risk for breast cancer for as low as just 2 drinks per week, less than that guidelines. Now, the actual absolute magnitude is very, very small at that level. So this is what gets that precision medicine, right? Like if someone said, okay, this much more, a little bit of an increased risk of cancer, you'll never get to 0 risk. Like this is an important quality of life thing. And actually something else to tailored medicine is, if you really want to geek out, I'm trying to focus on more super well validated data for you. I'm like an aficionado of all sorts of more evidence-based biohacks. And it's interesting, the pathway of alcohol metabolism can be modulated a little bit by sulforaphane. You see, isothiocyanate, ITC, in brassica or cruciferous vegetables. If you bite into it, myrosinase is released, And then myrosinase enzyme then dissolves, catalyzes, so it becomes sulforaphane. And in turn, that sulforaphane can actually bypass that pathway, so it's less to the mutagenesis pathway. So in theory, don't say, oh, Dr. Barzilai said it's fine to drink, just have some broccoli first. No, not, but just on a theoretical basis, there are certain things that are fun to geek out on. You're like, just for psychological, like, hey, it's fun, but it shouldn't affect your overall conclusion. So everyone should decide what's right for them. So let me illustrate this concept of precision medicine in a very concrete for you, Gil. Let's say someone is an ApoE4 carrier, either a heterozygote or homozygote. Remember, we have one copy of each gene from each parent. There are two alleles. The alleles come in three different variants, which the protein components are a little bit different the way they fold. And I won't geek out on the pathology, but the bottom line is you have increased risk of Alzheimer's dementia. And so these individuals would benefit from being more aggressive in terms of their modifiable risk factors, right? So this may include lowering the ApoB, prioritizing being at exercise, which might be in some ways the most potent intervention at the right dose, more aggressively. They would benefit. Sleep is phenomenally important, metabolic health. So targeting these things is very important in this population. Likewise, if we're talking about from a practice standpoint, for me as a physician or consultant, maybe you want to follow your amyloid levels or neurofibrillary tangles, your tau, phosphorylated tau surrogate markers to which you can see years in advance to monitor to see how it's progressing. And you might even consider plausible things that are low effort, like the data on cognitive training is mixed, but it's low. It may, like whether skill A transfers to skill B. There is some favorable evidence, but are you going to wait for that all to be worked out? It's like, no, if I'm high risk, I probably want to be doing that. And people can consider dietary wise, there's a version of a variant that's between the DASH diet and the Mediterranean diet called the MIND diet. It's similar to the Mediterranean diet in that it emphasizes extra virgin olive oil, for example, healthy fats. It places more evidence on things like leafy greens and berries, for example. Actually, it's fascinating because these phytonutrients in blueberries, like anthocyanins for that particular bioflavonoid, is localized in different centers of the brain with different functions. We don't understand half this stuff, but we see epidemiologically associated outcomes. So with precision medicine, it's here all these things an individual can do, and then depending on their values and their preferences, you can target accordingly. So another example, and this is also an area of controversy, at least in the conventional medicine circles, who are not as willing to go outside of standard current guidelines versus willing to see suggestive evidence. It's like it's promising, so let's do the best we can, even where there are some unknowns, is the use of continuous glucose monitoring. Like, for example, there's brilliant work out of the Weizmann Institute that if the two different individuals, their glycemic response to, for this example, white bread versus glucose, one individual may have a huge postprandial glucose excursion or glucose spike to white bread, and the other would be to glucose. And depending on their microbiome and other individual factors, they might respond differently. But using a CGM, a continuous glucose monitor, you can look at not just the area under the curve, but you can actually observe. You say, when I have this kind of a meal, this size, at this time of day, with this level of exercise, you start to detect patterns that aren't just global patterns, but that are specific to you because of those differences. Plus, it's phenomenally rewarding, like for you actually to see, and I've seen this on myself, like I've found for not just for myself what foods, what glycemic loads and caloric loads, but just taking even like a little walk, it's amazing. You just see the CGM, your Dexcom or what have you, go down. And that's incredibly positive reinforcement for this. So in essence, what makes precision medicine so powerful isn't just having a more tailored approach to individuals, but also this sort of, I took a graduate course on continuous quality improvement where I coached clients when I was a PhD, like how to improve their health through these loops. It was a lot of fun. But through these loops on yourself, first, find a target that makes sense. Second, monitor it, do surveillance. 3, make adjustments. And that dynamic adaptive response lets you hone in those variables more effectively.
Yeah. And just to comment on what you said about the CGM and the Weizmann, so the professor that done it is Ran Sigal. Yeah. And actually we had an episode with him, an early episode a couple of years ago that he discussed it in detail. Another point about alcohol. So my father is 93 years old and he's still completely functional. And my mom called me a few months ago and saying, your father wants to drink alcohol, and I don't think that is healthy. She's saying to me, I don't think that is healthy. He's asking if you are allowing him to drink alcohol. So I said, first of all, he's 93, so let him do whatever he wants. But second, as you said, David, there is a risk for cancer and other, but also there is a good data right now that it's affect your sleep in a negative way. So I told her, let him drink alcohol, but drinking at lunch instead of dinner, and then the effect of the alcohol will be less effective. So I think that that's another example of, let's say, precision medicine or personalized medicine that basically find the right thing that if a person really like alcohol, like your wife and my father, let them do that, but maybe adjust the timing or, as you said, biohack and provide it with something that will decrease the negative effect of it. So I really like the example that you
on
provide.
A full stomach, so it's slowly absorbed because it is associated with neurocognitive decline, which we have a decline, even at more modest levels than we previously thought.
And by the way, a couple of episodes ago that we released, we interviewed the person that actually discovered the GLP-1, and he said that one interesting effect of the GLP-1 drug is that you see people that are less, the effect of alcohol on the body is much lower because the alcohol stuck with the rest of the food, and it's taking more time for it to be released. So they are actually less affected by alcohol. So
it's fascinating and it's complex. It gets back to the precision biology, right? Like the dose matters for what we're talking about. Like if it was more than one alcohol a day, I'd be very supporting and loving, but we would talk based on it, because that's when it really starts to become more significant. And like when we're talking about precision medicine, on one hand, if you have one person may benefit from something more aggressive, like for example, if someone carries like a BRCA mutation or a gene for Gardner syndrome or something else, they might benefit from earlier screening. There was a study out of Health Nucleus that about 1.7% of asymptomatic individuals end up having a tumor detected, and more than half of those turned out to be malignant. Now, if you have a family history of cancer or something like that, maybe you should be like the guidelines for some cancers are to screen 10 years early. And I would say screen now. I don't care how old you are. And then adjust the surveillance level. On the other hand, for your father, it's like the story you told me of your father. I love it. It reminds me of a movie I saw. It was one of those like alternative movies, you know what I mean? Like from one, like a small film award, but it was about this lovingly dysfunctional family. And one of the people there was this grandpa. He was like, he had very poor health, and he was like constantly like taking hard drugs, and his grandkids like, you have to stop. I have to stop. I said, and I'm changing the facts a little bit, but it's along those, like, I'm 90 something years old. Everything hurts. I believe nobody should take drugs their whole life, but when they turn 90, we all should be taking drugs. We all should, you know what I mean? Like when you're at the final stages of your life, it's like, you have to take into account this sort of quality of life metrics. And I'd actually love if you let me to dive into some specifics. Since I went very broadly, I'd love to go into the specifics and how a personalized health plan actually can extend health span and lifespan.
Let's do that. I think that's fit very well with what we are talking about. So let's dive in.
Yeah, so people tend to gravitate to facts, or at least data, because facts and data are different. As a scientist, you need to be skeptical, and you need to remember that many of the statistics some are counting are from observational studies, which often tends to bias towards a positive effect size, although I believe in most cases are at least directionally correct, that is, in the right direction. So one key biomarker is your aerobic capacity, which people might have heard of their VO2 max. So depending on what study you look at, individuals who are in the top in the top percentile for their cardiorespiratory fitness, they have a 40 to 80% associated reduced mortality, which is huge between that percentile and that percentile. In total mortality, it's hard, we find in study in epidemiology even, to show big differences in total mortality. We can prove it for disease specific. And another way that's been represented is for every 1 MET improvement in your cardiorespiratory fitness, that corresponds to about a 14% increased, about a 13% increased or decreased mortality rate.
David, can you explain to our audience what is MET? What is metabolic equivalent?
I think more memorable than the mathematics of it, because I would need to go into high physics.
Level,
high level. I'll give you a feel of it. The current recommendations discuss between like 150 minutes per week of moderate physical activity as the minimum guideline. You actually get a lot of benefit even below that, and by doubling it, you can get even more, and by tripling it, you can get even more, although diminishing return. And as you mentioned, there's a J-curve for benefits and trade-offs. So if you're thinking about METs, if you're on an exercise bike and you're pedaling away, moderate physical activity is typically between around 3 METs and 6 METs, between 3 and 6 METs. So now assume you're pedaling the bike at 3 METs, which is at the lower level of moderate activity, for an hour. That makes a MET hour. It's a multiplicative, MET hour. So if you're doing that 3 MET hours for 5 days a week, that's 15 MET hours per week. That's already double. That's already double the minimum level guidelines, which is the equivalent of about. These are estimates that actually, it's not an exact translation. The minimum is about 7.5 MET hours. And actually, I can tie that into another statistic, lest you be intimidated when I said about up to a 40 to 80% reduction in total mortality from the fittest, 2.5 percentile to the bottom. What if I just told you, all you had to do is to achieve approximately 7.5 to 15 MET hours. So just about 150 to 300 minutes of moderate physical activity per week. Even that individual was found in one study to have a 31% reduction in risk for total mortality. So you can see you get much less benefit from being like average or a little above average and like being super duper than just going from being a total couch potato and starting to move and then like reasonable. That's where the curve's like insanely steep. So I would keep that in mind. So that's exercise. We want to talk about, of course, about your hemoglobin A1C. We talk about ApoB, right, which is, you mentioned that's more accurate than LDL for cardiovascular risk because it incorporates things like Lp(a), chylomicrons. It's total risk across multiple particles with a particular receptor all attached to all of them. So ApoB and VO2 max and hemoglobin A1C, that's another marker of metabolic health. So what we find that for individuals who are, how should I say, hemoglobin A1C is a marker for your average blood glucose level, okay? We've all heard of glycosylation, which is just an enzyme doing something on purpose. There's also glycation, which is just like you have these age-associated modifications of molecules where they have these sugar moieties that are associated with them. That's advanced glycation end products, age byproducts. So the higher your hemoglobin A1C, it's just a reflection of how many advanced glycation end products you're getting globally across your body. It's not that just the glycating hemoglobin A1C is bad for you. It's that it's a way to measure overall what average blood glucose levels have produced, and the higher glucose levels, the worse it is for you for that reason, and a whole bunch of others having to do with insulin signaling and inflammation and so forth. So for every 1% improvement in your hemoglobin A1C, you have about a 14% lower risk in total mortality. So you might say to yourself, well, that's for diabetics, right? What about for healthy people? This particular study where I gave the statistic that a 1% reduction in hemoglobin A1C reduces total mortality by 14%, their lowest reference range for those with a hemoglobin A1C 6% or under. Now, diabetes is only defined at 6.5 or higher. Pre-diabetes is like 5.7 to 6.4. So if you can imagine the lowest reference range under 6, it really started at it included some people where there was low as like 4.8, you know what I mean? Okay. Below average. And it overlapped with pre-diabetes and even some healthy individuals in that group. And that relationship was still maintained there. So if there is a threshold for lower hemoglobin A1C being better, it's below the diabetic level, certainly. So I think that's very relevant. And another area is sleep, right? Now, this is, again, like, how I say, take with skepticism observational studies. I'll take this with extreme skepticism, the effect size of this, which is a way of saying the magnitude of an effect from a biostatistical standpoint. There was a study that found that individuals who are short duration sleepers, they had approximately a 47% increased risk for cardiovascular events and mortality. Now, I think that's, you have a lot of people there that are getting poor sleep because they're sick, or poor sleep is indication of other things in their life or other things about them. So I don't think it's going to be likely to be at that level. But I think sleep has a profound impact, and I do believe it has an impact on total mortality. Its exact size isn't known, but it's certainly, when we sleep poorly, our cognition, we're metabolically, we are less insulin sensitive. We have poor lifestyle choices, and actually low sleep does other things too. Low sleep actually affects our hormonal health, and low sleep also it promotes inflammaging or chronic inflammation. It also it basically affects a lot of the hallmarks of aging. So I think the big picture is to remember. And by the way, I mentioned Life's Healthy 8. There's more than one kind. There's one from the American Heart Association, and there's one from the VA study I mentioned. But the ones that they share in common in the Healthy 8 are, of course, diet, exercise, sleep, and stress. And then you have other ones that fall in different definitions of Healthy 8, which might be opiate use or abuse, excess alcohol use, smoking, social connection, or for the AHA criteria of Healthy 8 includes having a healthy range, blood pressure, which is another area where being even on the lower end of the normal range, you tend to continue to see benefits, or to have lower ApoB levels, which is another area where to be even on the lower ends, there's there's solid evidence that there's always to a point, right? But being on the lower side, even if you're normal, for most individuals and circumstances is usually better.
Yeah. And I think that similar to the hallmark of aging, all of those variables of sleep, exercise, nutrition, stress are interconnected in a way. So if you are not eating well, that might influence your sleep, or if you exercise too late, that might influence your sleep. And if you're not sleeping well, it's less likely that you will go to exercise because you're too tired. So I think that all of those are interconnected, and it's important for us to find the right routine. And what is nice about it, that a lot of it is under our control, not all of it, but a lot of it. And people can optimize their health by and hopefully longevity by doing that. But now I would like to switch gear and talk about longevity-related drug and supplement. We spoke about it a bit. We spoke about rapamycin and metformin and other. What, in your opinion, are the most promising, and if you can say why?
Okay. So, of course, I would start with what is most evidence-based. Where we have the most solid evidence are simply ensuring the nutritional adequacy. And this is an area where I think medicine can improve, like how often are we checking vitamin B12 levels? You don't need to be a strict vegan to have low levels. And it's so vital to cognitive health as a variety of other factors to have adequate B12 levels. Vitamin D is another area that, ironically and interestingly, the Endocrine Society recommends against testing. And they recommend basically, this is as of 2024, their updated guidelines. You need to stay up to these. The guidelines as a longevity medicine provider, but then reading broadly, sort of have your own take on the literature because it's not godsend. So, but basically, they were recommending more empirical treatment. But I do believe a minimal level. It's clearly that when you're deficient, although the threshold isn't as clear for vitamin D, exactly the threshold, deficiency is very bad. So it's not just there have a whole bunch of observational studies from everything from...
Well, one comment about that,
yes.
David, I think that those two are very important. By the way, those are two vitamins that I have an issue, and I'm testing myself using Instant Tracker almost 4 times a year. And still I'm struggling to balance them. And when you look at the population-wide, you can see that almost, I would say, between 30 to 50% of the population have low vitamin D. Again, depending how you measure it. And for B12, it can be in the 10% or something like that. So it's not very small. And I agree with you 1%. They are very important, and that's something. It's not a rocket science. It's like just the basic.
It's not, and it's getting harder because from the Institute of Medicine, I was privileged when I was getting my PhD. I had not one but 2 advisors in the Institute of Medicine, which we now call the National Academy of Medicine. Incredibly hard to get in, prestigious society where they advise Congress and agencies about what best practices are, but you're referring to having a 30 nanogram per milliliter minimum levels, which was the traditional optimal level, and the Endocrine Society anyway are now sort of saying, well, it's not clear there, just treat empirically. But I do think that the bottom line is it is reasonable. There are reasonable limits, even if there could be some controversies exactly where to set it. And as a longevity provider in precision medicine, I'm interested in not just having adequate level. There's one thing between having a sufficiency and having an optimal level. This is something that Bruce Ames, who's known for the Ames testing as a quick way to sort of have a good guess about what might be toxic in a human. He was an extremely dynamic person. He came up with the triage theory of aging, where in his triage theory, it's like, well, you have some nutrients that if you're above a certain level, then you're no longer deficient, but you're no longer optimal because the level is still so low, your body uses it for 2 different purposes. And because your body uses it for 2 different purposes, that nutrient is not going to be adequate for the other purpose. So there is one thing having inadequate vitamin C to get scurvy or vitamin D for rickets. The optimal level for vitamin D might be at a level that's higher than just above a safety margin for rickets. So if we look up Bruce Ames, and there are all sorts of interesting applications like vitamin K2, which has its own controversy because it's interconverted with vitamin K. And anyway, there's the bottom line is there's a big difference between sufficiency and optimal, and what's optimal may depend on the individual. So as we continue to go down the rabbit hole of things that are controversial, that I'm at the current state of mind as a scientist, I always reserve the right to change my mind because I'm actively every day reading the literature and making adjustments for as needed based on the preponderance of evidence rather than overreacting to any one study. Another example is what we call omega-3 fatty acids. They are essential fatty acids. We absolutely need them And modern diets are a lot richer in omega-6s than they are in omega-3s, where historically we were seafaring and we ate a lot of seafood where we got a lot of omega-3s. So it's not surprising that our omega-3 levels are lower, not just than our ancestral levels, but also lower than some populations. Like in Japan, though hypertensive stroke is more common thought to be due to their high sodium diet, which is something else I should mention as a risk, but they're lower risk for other things. And one of the hypotheses for that is their higher omega-3 levels. So not to make this a naturalistic fallacy type of thing, our ancestors could have done things that were completely awful to them. What's natural isn't always good. There are plenty of things that are unnatural that are good, and there's plenty of things that are natural that are bad, like cyanide. But for EPA and DHA, for cardiovascular health and protection for neurocognitive decline, and we all get some decline over time. It's a pretty predictable for mild cognitive impairment, even if only some become dementia. Those two levels, as reflected by something like your omega index, which is one way to quantify, to standardize it compared to other populations, a lot of us are low. Now, the data on it is mixed, and some critics are saying, well, if your level is too high, you have too high AFib. And then the counter critics are saying, yeah, but you're getting fewer heart attacks. So who cares about the major league heart attacks? Although you can also get strokes from AFib and other problems. And it's possible that it has one protective and one negative at the same time. We could take a super deep dive into the studies. Like, for example, one study that found a benefit for a more higher EPA to DHA ratio, say, well, they use this control mineral oil, and mineral oil looks like it raised some lipid biomarkers, triglycerides may increase their risk. And then there was another study afterwards that we took into account that mineral oil was a bad control, causing problems to the control, and still we have this amount out of control. And I was like, if you're not doing mega doses where AFib becomes increasingly more of a concern, to have something that's a reasonable level, and this is in the realm of opinion. I try to be very clear as a scientist and as an evidence-based physician, the difference between opinion and fact. I'm giving you my opinion that for most individuals in most circumstances, to have some minimal levels is a way to sort of hedge bets, even with the uncertainty, and for biological plausibility and some evidence along those lines. So now there are a million things, people, that we don't have time to go on to. I think there's taurine, there's glycine, there's AKG, there's spermidine, there's urolithin A. Are we talking like senolytics? Are we talking things that are relatively more like? There was one really great study with taurine, but it's only one study. I want to see it reproduced with like a 30% lifespan extension, but it was not an interventions testing program study. It was extremely rigorous, but it needs to be validated, and human equivalents might be as low as 3 to 6 grams, but I'm not going to make a global recommendation. People tend to talk about these interchangeably, Gil, like they're all the same. Like, yeah, I take taurine, I take glycine. Well, if you want to take glycine, remember, it's only about on the order of a 4 to 6% lifespan extension in the interventions testing program, where it made up 8% of calories. So you want to take 50 grams of glycine a day for the equivalent of it. And their effect sizes are very different. And some of them have relatively short-lived controls. Like there's a 900-day rule. It's not a real rule, but when you have short-lived controls, you believe it less. And I love Brian Kennedy. I want to see AKG studied more in human organisms. But if you look at it, the controls are relatively short-lived, and the effect was modest, particularly in males, whereas females more. But I think that what was more provocative for AKG, you saw there was a metric for health span. It was a creative way they did it. We don't have time to go into it. That shows more promise there. So I think it should be studied in human beings. So that's all, some of the stuff over the counter. Like if we mentioned before ApoE for carriers, there was a study that I'll give you 2 examples of supplements that I think will be interesting for the listeners, because it's relatively relatively higher quality evidence. One of them is curcumin. God, I hate mentioning particular companies, but curcumin is so low bioavailability. Even if you take it with black pepper, which has piperidine, which increases bioavailability 1,000-fold, that's not necessarily that reproducible. It hasn't been a very reproduced effect. When you take it in supplemental form, it usually doesn't do a very good job crossing the blood barrier, lest of all being absorbed, which is the big problem with most of the formulations. There was a particular one where they followed individuals, and this was a placebo-controlled, randomized controlled trial, not these off-label indications, which is the norm for most supplements. They found that individuals in the intervention group did seem to do better for neurocognitive testing. And moreover, interestingly enough, they also did a PET scan of the brain specifically for amyloid level, and the intervention group also had a lower burden. I'd love to see that reproduced with a larger sample size, longer trial, and so forth. So I don't take it as definitive. But if I was an ApoE4 carrier, I'd seriously consider that. And another example of high quality supplement is creatine monohydrate, which for athletes specifically, along with caffeine, basically those creatine and caffeine are the real validated ones for athletic performance, particularly if it's like a power event where you need to really perform for impulse. To some extent, there's some evidence for strength too, but especially that because of this high energy creatine phosphate impulse energy. And there's a little bit of evidence. It's not as validated that possibly may cognitive benefits or prevention from neurocognitive decline. If you're deficient, vegetarians tend to have lower levels. So that's the latter claim is maybe, like let's continue to study, but for the impulse performance, definitely. And then the last of the supplement, more quality, before, if we have time, I can go to canagliflozin, is the Cosmos study was, they have a cocoa flavonols. And this was a huge study, a randomized controlled trial. And basically what they found was that they had fewer cardiovascular events, not total mortality, which wasn't their primary indicator, but by like 27% in the intervention arm. I mean, it's an NRF2 activator, stress response, antioxidant defense, mechanistically, so it's plausible, but I think that's one of the most undercited study there is. So if people choose to have cocoa products that aren't in a validated supplemental form and they want to have the equivalent, I would just caution them that a lot of chocolate products are high in heavy metals, cadmium in particular, which is associated with degeneration associated with hallmarks of aging. And I do think to get it at that level, you need to have something better sourced, such as a cocoa from Tanzania. But really, I would say make sure it's third-party tested, which is a whole other thing. Like people are taking all these supplements without third-party testing, and they're just believing them. And even like pure encapsulations, like as a rule of thumb, I'm just using as an example, not to pick on pure encapsulations, because I really like pure encapsulation products, but there was a study was either by Consumer Labs or Consumer Reports. They both do their own third-party testing. They found that their ashwagandha in pure encapsulations wasn't at the level claimed. They also look for impurities and other issues, and it's totally worth supporting them. So you have to do your due diligence for supplements, and we don't have nearly enough time to talk about all these different ones. So with the remaining time, I would just like to briefly mention canagliflozin as an exciting prospect because it unifies so much of what we talked about. In the interventions testing program, one of the things they tested was an SGLT2 inhibitor. It's also called Invokana. It's already used in diabetics. It's a sodium glucose cotransporter inhibitor, and essentially it works at the nephron level and prevents reabsorption of glucose. So what ends up happening is we end up peeing out more glucose. So in humans, it lowers blood glucose levels. Well, in mice, without really substantially lowering blood glucose levels, in the male mice, in the highly rigorous interventions testing program, it extended longevity, not one, but several interventions testing programs at different ages in life and at different doses. Now, only in the male mice, I know people are going to ask later, so I have to say briefly, why only in the male mice? Rich Miller's lab looked into this, and it looks like because it gets like super high concentration because of differences in metabolism in the female mice, which may be toxic, and at least one study may be associated with a particular kind of GI malignancy pathology. Here's the good news. I took a deep dive on my own. I do these deep dives for myself and I have a few clients I take on, and the human levels in males and females were within the range for the male mice, not the female mice that didn't benefit, that might have that thing to offset that problem, to offset it. So, and they've also looked at things like locomotor activity, grip strength, rotorod performance, all these different health span metrics. And the mice were doing better for this too. So, all of these, so that's canna. So how about for humans? Well, in humans, interestingly enough, well, as you'd expect, it reduces mortality and diabetic complications in diabetics, right? But they also found in humans that canagliflozin in populations with heart failure, it reduces rehospitalizations from heart failure. And in non-diabetics, and it also, and I'm not talking about here, I need to qualify. This wasn't a study on canagliflozin. It was another SGLT2 inhibitor. So I'm talking about them broadly, okay? And then there was other work that not just for heart failure, but for individuals who have chronic kidney disease, for whatever reason, for reasons besides diabetes, it slowed down progression. So we have some FDA indications for that also. So is it possible that this is working? We already know it puts less stress on the nephrons, so it kind of, they burn. We have like nephrons are like brains. It's a post-mitotic, like we have them for life. They're not divided, and we're still holding on to them. So when we lose a nephron, and every year we're losing nephron every year, that's part of aging every year, all of us. I don't care who you are. We're not reverting that. They only die, okay? So if we can slow that down, even in a healthy person. So this to me is has a potential off-label use, just like in Joan Manick's study with Lloyd Clickinson in 2014, when they used everolimus rapalog, that intervention was suggestive. And there's been lots of other things that have been studied for rapamycin from across animal models, but for humans, that's just another example of something that has potential. None of these are just endorsements. They're all sort of like things that we should be studying, and in a precision medicine, perhaps considering with a specialized, unbiased, objective, qualified health professional. The pros and cons in lieu, because we're all going to die, right? So the decision, I believe things should be true and proven safe. I think safety is very important, and you need an appropriate safety to efficacy ratio. And I think it's much more complex where old regulatory systems like safety, efficacy, things that work. But if you're slowing down aging and you're going to die anyway, and if you're willing to, is there some amount of risk that it's reasonable for individuals to incur for unknown, where it might not help, it might even hurt, or it's known to hurt this amount, but we're willing to hurt this amount for X probability that helps that amount to the best of our ability of estimating based on modeling, which is an inexact science.
Yeah. No, thank you so much for a great overview of what is happening, starting from something as simple and maybe call it boring as B12 and D, and going to SGL2 and getting into something that is just evolving and getting ready to and have I think that a lot of potential, as you said. I always say. Sorry.
Oh, I know you're going to ask me a great question, but I know that people are going to be upset if I don't mention a particular topic that's kind of related to this. It's like, he didn't mention epigenetic reprogramming. Is there anything to that? Because that's just so hot right now. I mean, okay. David Sinclair by far has been the sort of leading to public awareness of the field of aging biology, and this is an area that he, there's early work by Ocampo where before we knew that there are these Yamanaka factors, by that name, Yamanaka got a Nobel Prize actually for discovering these 4 OSKM factors, which are transcription factors, that if you give cellularly, they can revert cellular identity to an earlier point, where at least in isolation, it leads to 2 processes, right? One is you have a reversion of some of the age associated phenotypic markers. So you're kind of unscrubbing some of that, what's known scientifically as epigenetic drift since getting younger. But at the same time, something else happens. The other thing is they're also getting de-differentiated. So they lose their cellular identity when used in isolation. So that's not good because we don't want to turn it to stem cells or we don't want to turn it to cancer. And early studies found that there were teratomas in attempts to use this for aging because we couldn't uncouple the two. Then Ocampo was the first to find partial epigenetic reprogramming as a tool or technique by which you can maintain cellular identity while resetting is maybe a strong word, but some reversion of these epigenetic markers to a more youthful state. And it was amazing that this was a genetic model, so it's not like ready for prime time for human beings, but he had an inducible system where Yamanaka factors were released when you give doxycycline. And those mice lived 30% longer, and they also had better tissue regeneration. Like if you cut them, they regenerated also. So this is incredible, looking at it in terms of reverting some markers of keeping cellular identity without tumors while setting back the clock, at least partially phenotypically, for the epigenome in a substantial way that increased survival. Now, what David Sinclair did, I want to say around 2021, had an experiment, had several different arms. He crushed the optic nerves, exposed to kind of glaucoma-like pressure circumstances, but also just naturally aged mice. This made the mice blind. And what he did is he used a different system. He used adeno-associated virus as a vector, and for 3 out of the 4 Yamanaka factors, OSK, because c-Myc can be more oncogenic, and it still worked. He was able to revert to help rejuvenate retinal ganglion cells, and you can actually see them kind of regenerate, and these slides that he has. And importantly, they were able to regain some of their eyesight. I mean, this I think is phenomenally exciting. Now, we need to remember, like when we talk about can we revert these processes, it's like, can you turn back the clock? You need to, well, there's still, of course, extracellular damage, right? And there's other forms of damage, there's DNA damage and so forth. But to me, it's exciting work like this from not just David Sinclair's, but many other labs in epigenetic reprogramming, which shows a lot of potential, as well as things that we used to think aren't possible, even from run-of-the-mill rapamycin. We used to think about rapamycin, great, it extended lifespan, it must be slowing aging. And what Matt Kaberlein found is, and there's evidence that it does slow biologic aging beyond lowering cancer rates. Rich Miller shown it increases tensile strength for the tendons and reduced fibrosis in different organs, other phenotypic changes resembling younger mice. But another interesting thing that we didn't think we used to be able to do was one study with rapamycin studying in the oral cavity in mice is it didn't just have an oral microbiome more similar to younger mice. It's like maybe, and reduced inflammation, but you actually had periosteal bone regrowth. I didn't say you lost less, we had regrowth. And there was another study, Matt Kaberlein did actually a couple studies like this now, but at least in his initial pilot study for dogs, different species we established have different top causes of death. Doberman pincers have a particular kind of heart failure and so forth, and larger dogs have more insulin IGF-1 growth factor and mTOR activity, which is one reason that the larger dogs, which are also shorter lived, are being studied by Triad from the Dog Aging Project. But anyway, what he found, even before all this, was if you give rapamycin to these dogs, the cardiac function, the heart needs to relax and it needs to pump. And what he found was that the E to A ratio and the ejection fraction, which are markers of diastolic function or relaxing, and systolic function or pumping of the heart, both of them physiologically improved. So they were looking at these ultrasounds of these dogs. You give them the rapa, so it's not like their heart failure slowed down, but their actual physiologic phenotype, which can translate to quality of life too, right? Like we all know people who have angina doing the stairs. It's a different condition, but so to me, these are exciting potential pathways and I don't think it's going to take one. I think it's going to take, to get furthest, fastest, we need to take a wide variety of approaches. Some will work better than others, but using them in concert is likely to ultimately be more effective in this question.
Yeah, that's amazing, David. And unfortunately, we go to the end of time. So thank you so much, David. And I will talk to you offline. Maybe we can have another episode to cover what we haven't covered. So thank you so much again. And we are looking forward to explore the research in the field of longevity each month with you and the other leading scientists. For more information, please go to www.insightracker.com/podcast.
Thanks for listening to Longevity by Design. Please subscribe to this podcast on Apple, Spotify, or YouTube. Longevity by Design is powered by Inside Tracker, a personalized health optimization platform that helps people improve their lives by improving their bodies from the inside out, using personalized, science-backed recommendations for nutrition, supplements, and lifestyle changes. To learn more, visit insidetracker.com/podcasts.